for example, this species here is one of the ones that's in the phylogenetic analysis. You'll note that it's currently called Undaticintus. I don't even try to pronounce it properly. That would be my best guess. We have 0 occurrences of this particular species with that genus species combo. It's under 2 others, but because of the taxonomic tables, it is connected. So what's going to happen is, while it was reading through the Nexus matrix, or the Nexus file, and getting the taxon names, it was taking advantage of this information. And there will be a flag if there are some taxa in there that are not in the taxonomy tables. And again, if you were doing this sort of stuff, you're exactly the sort of person who should get involved and enter it. And you might even have your own opinions on this. One other thing it will do is, if you have 2 taxa in there, one of them is considered to be a junior synonym of the other. Many times people have used phylogenetic analyses as sort of ways to assess ideas about a synonymy. What will happen is it will pull out the junior synonyms occurrences on their own. It will temporarily relax that synonymization, so you can get the information independently. But here's the important stuff. This is where all of these species were occurring. And then what it's going to be connected to, as I said, is a big collections table. And this is basically the sort of stuff you would get from the download. Now, one big difference: the early and latest interval are no longer the ones that are reported by the Paleodb. They're now going to be in the units of whatever stratigraphic scale you requested. It will convert them on over. There's information about the references. This is all standard Paleodb output. The way I have it set up, in case you're wondering, that's the Burgess Shale, yes. The formations, rock groups, etc., the zone information. In addition to the usual Paleodb output, it's going to append this with information about the rock units from the rock unit database I put together, including sometimes where people have been inconsistent and said, well, it might be in one member or another, and basically putting on the upper and lower bounds of that collection based on that rock unit, and if there are any zonal taxa there, either reported in the zones or as part of the collections list, restricting it with that. And yes, if there are 2 different disjunct zone taxa reported at a community, then basically what that's going to say, it has to be within the ranges of those 2 zones together. So it's not going to necessarily sync it into one. And here's your zone information. Now again, why am I telling you to look at all this? If you're someone who's focused on these groups, you're going to be in the best position to go, that's no longer the Stevens formation of that area. It's, lateral equivalent with a different name. Other sorts of information that might be on these things, it might be in here that you now know is outdated because you have been doing sort of the homework paper trail, or now electron trail, of trying to keep this information updated. So as I said, that is going to be important to look at. But this is also where we're going to start outputting our first stuff that RevBayes really wants. Now, I showed you this in their tutorials, what it wanted for bears. Well, that's in the sort of simplest version that they have. Here's sort of the first thing like that, its output. Why are you telling me this? Okay, that's fine. I don't really care about the spell check right now, thanks. And what this is giving you is the min and the max based on the distribution of Paleodb finds. Now, this is the min and the max. This is the oldest possible date from the oldest time unit or zone, and the youngest possible date from the youngest time unit or zone. We're not going to use this. Why? Well, partly because of the way RevBayes is set up. It wants 0 to be now. And if you want to run through the program, it's basically going to be taking into account the 500 million years that have elapsed since we last saw them. It also then is going to want the, what is the sampling rate of modern synktons? Well, synktons might be hanging out with Elvis somewhere. If so, they have a sampling rate of 0. It doesn't want sampling rates of 0. That causes things to blow up. So the usual tactic instead is to rescale them. So here we are. with the dates rescaled to the latest possible last appearance of any of these guys. And what you're seeing is the oldest ones are getting up to about 9.6 million years older. And that's actually with the outgroup that's in there, and a variety of other dates. Now, currently, there seems to be a bug in RevBayes in which it is using that min and max, and this might be a bug, or it might be sort of a difference in the way that people who are looking at these dates were thinking about the fossil record. Basically, it seems to get treated as a possible upper and lower bounds, and what you often get are divergence times for individual taxa after their first appearance. So it's treating it like it's a fuzzy range. And if you're used to thinking of a fossil record in which, like most dinosaurs, where you know them from one locality, and it's sometime in the Albion, and that's all you know about it, that would be appropriate. But in this case, it really isn't, because we can tie down points by which they definitely were present. So what I've set up in the interim is just a file that resets it to everything's first appearance. And both the min and the max are set that way. Hopefully this won't be necessary in the future. But what this means is you don't get divergence times that are after we first find a taxon. And that's nice. And it's now slightly changed in terms of what's 0, because now 0 is going to represent the latest first appearance of one of the taxa. But this is a file we can use for basically setting up the fossilized birth-death model in current versions of RevBayes. What will be happening soon, and I think they've got sort of the preliminary codes in there, but it's not set up, is basically doing something to be a bit more intuitive, and that is putting upper and lower bounds on the possible first and last occurrences. So if you look at what we have here, sort of the max and a min for the minimum, the outgroup taxon here, the final species are known somewhere in the range of 3.5 to 4 million years before we stop seeing the clade. The first appearance is restrained to 9.5 to 9.6. That's pretty handy and tight. And what we see for several of these taxa that span multiple trilobite zones, basically there's some point by which it had to have appeared. It had to have been there by 7.5, and the latest it could have gone out is 4. Definitely out by 3.5. As I said, this isn't in the version of RevBayes that you could download and use today, or it's not usable yet. It will be soon. One other way that can be done that I think is available, but I don't think was anticipating a fossil record like this, is a version in which you can sort of split up the different occurrences and their ages. And so what I had the program do here, this isn't actually all of the occurrences. This represents all of the individual rock units from a particular trilobite zone from which we've been finding these things. So this could create some issues, particularly with fairly well sampled groups like marine invertebrates, because of a classic rule of nature. You get a lot of rare things, and you always have a small number of taxa that are really widely distributed. So what you wind up doing is taking Gyrocystis platisa here and dividing it up into 10 OTUs. When I was young, hip people referred to the taxa you're studying as operational taxon units. I've gotten the impression that's kind of outdated, but I'm a 90s guy. But it's dividing up all of these things and giving you an idea of where the particular occurrences are falling. Now, I should point out that there are some very new versions. For example, Rachel Warnock, Tracy Heath, and Tanya Stadler just published a paper in Paleobiology within the last few weeks that would actually want to use this sort of information to get a much tighter idea of the sampling densities within the ranges and come up with a much more, I think, elegant and appropriate model for estimating the first and last appearance times. So it's possible that this sort of thing will be useful in, or more useful in a less cumbersome way in RevBayes and not distant future. So that's the stuff we're getting. So that's part one of what we need. So at this point, I'm going to stop sharing and see if I can get questions for a moment. Questions? The repeat authors on the paper from the last one, that was Warnock, Heath, and I think it's like in first views in paleobiology right now. Someone else beat me to it. And Rhea is pointing out to everyone that agnostics are definitely a sister group. See, that's why I have it set up there, because, you know, I don't know if we have that opinion in there yet, but when it does get in there, I'm ready for it. And let's see here. And yes, it was not an issue with it not accessing the Paleodb. There are times when it's down for servers. It was because I forgot to grab all that information beforehand. So I was going in there without any idea of what the onset was. Actually, it will put defaults for a lot of those things, which will let it run. But in this case, the default, which was probably like the Archean, was really, really inappropriate and made a mess of things. Let's see. The times in the Paleodb are originally determined by the I can just show you this real quick. And again, it's sort of rehashing things that Mark and company have shown, but I can just, it's one of the fields where it's going to be the sort of a minimum interval and a maximum interval. There we are. And geez, shocking. The most recent stuff was entered by Matt Claflin. What were the odds? See, there's a good example of Bayesian friars right there. And we have a sort of maximum oldest time interval. If it's possibly spanning 2 intervals, you would enter a separate minimum. And in this case, that for this particular collection, it will be assigned a lower and upper bounds that coincides with the late/upper Albion as it's presented in grade scheme 2012. Now, again, what would be different for the stuff I have from here is that it would be taking a rock unit, although that one didn't have one, and any zone information, trying to tie it down more exactly. So any other questions at this point? All right, back to screen sharing. So we've output this information. This is going to be the first thing. Now we're starting to cross into the RevBayes territory. This is the first thing that's going to want to use. We are now going to get some estimates of the sampling. And what this is doing is estimating the sampling based on the distribution of finds in collections first and rock units second in the individual time intervals. Moreover, this is not just an estimate based on like the average number of collections that are occurring in. What it's doing, using that for sort of a uniform distribution, but it's also looking at distributed, basically distributed sampling rates, exponential one, a log normal, and a beta. And what it's going to do is sort of take a weighted average of those based on how well they fit the model. This is actually fairly important because, as I mentioned before, we have this wonderful rule in biology where you always get a few guys who are just, you know, very, very dominant in terms of lots of occupancy, lots of finds, and then some sort of exponential drop. And what this means is that the arithmetic mean, and that's where you're usually going to, with a lot of these sort of uniform sampling rates, is much higher than the median. And we can take advantage of this to sort of focus on a median sampling probability, which is, I think, much more appropriate. This said, you could do this any way you wanted. This is just the way I'm having it done for this particular example. And again, what I really want to do is show off what you can be doing with the Paleodb to get yourself started for things like RevBayes. We're also getting one important number from this that we're going to use in the end. Rho. Oh, that's pretty low, but probably appropriate. This is what RevBayes is going to use for the sampling rate for the present, for the latest appearing taxa. It's a pretty low number, but I think they actually last appear in an interval that's not terribly well sampled. There aren't a lot of rock units. And this is also based on an average of what you get from the sampling rates from collections versus those from just the rock units. You could do this another way. You could put in like a Chow-2 estimator if you wanted instead. There's a few different options. You would have all the information here for doing it. These are just particular ways that I'm doing it. Again, the emphasis being on what we've done is we've taken a Nexus file that someone might have gotten all the information from the Paleodb, tied down the ages a bit more than the Paleodb itself would, and output it like that. We're also going to get a quick and dirty shotgun estimates of the origination and extinction rates. Why am I doing this? Well, origination and extinction are going to be important parameters. However, as I'll show you, RevBayes is going to try to work them out on its own. It's going to vary those things freely. I'm doing this with the idea that if you seed the analyses with realistic numbers, it might speed up the time it takes for these searches to do what they call converge. That is, get to the point where you're getting generally good answers and your tweakings of your hypotheses aren't greatly improving things. In principle, good thing I have wood here, if you start off with good values, it'll take less time. And of course, this is also being done very differently. The estimates here are based on sort of population ecology approaches with the sort of underlying philosophy capture, mark, recapture. The rates as calculated in RevBayes are closer to epidemiology models, where you're looking at branching times in particular with specific ideas of ancestors and descendants. But this is just to get it going. And because, as I said, this is sort of a machine gun approach to get the general one, is assuming the sampling numbers got before okay. If you were really doing this for a paleobiology paper, you'd want to have all of these things varying. But again, I'm trying to help get things going for a phylogenetic analysis. This next part here, we can skip. What I've done is had it output the files as you went along, so you could just pick up at that point and reread the files. But we've started from there, so we won't bother doing that. What we're now going to do is write the, we're going to write the Fbd script. And because I have done this in a fairly modular form, we're going to be asking for this matrix one more time. All right, so what did I just create here? This is a script that RevBayes will use to parameterize the tree search part of the algorithm, and also to parameterize the diversification rates and the sampling rate parameters that it's going to vary. And what RevBayes will do is it'll take speciation rate. This dn exponential, 0.649, this is basically going to tell you that it's going to use an exponential distribution with an average of 1 over 0.649 to start as a distribution along which to look for the speciation rates, the cladogenesis rates. These moves here, and I'll show you this, an example of what this is going to be talking about for those of you who have not worried about Markov chain Monte Carlo searches. This is telling you about the different changes to a standing hypothesis. And remember, this is going to be a hypothesis about evolutionary history, the relationships, the divergence times, the rates of character change, and the origination, extinctions, and sampling rates that go with it. And what this is saying here is, well, we're going to make small changes, we're going to make some bigger changes, and we'll try some crazy, really big changes once in a while. What the weights are telling is essentially the probability or the relative probability we're going to do this. There's sort of two ways you can do a Markov chain Monte Carlo search. You can have each move get a set number in every generation, or you can have it done probabilistically. In the case of RevBayes, it's going to be probabilistic. But what this is saying is the small move is going to have 5 entries into our Polyas urn for the MCMC to look into to see if it's going to make a move. The medium move is going to get 3. The big crazy move is going to get 1. And in the case of RevBayes, it is done in a probabilistic fashion. So you might do nothing but make big changes on the speciation rate for a generation. You probably won't. What I have set up as well, and this is a little bit different from the way it's done in most RevBayes modules, but again, this is paleontologist speaking here. Instead of having an extinction rate set up as its own freely varying parameter, I have a turnover rate set up. And this is because when this is something that Charles Marshall talked about in his 5 laws of paleontology, extinction rates and origination rates are very strongly correlated within clades. And basically, you really don't want extinction rates that are too far off from the origination rate most of the time. Exceptions to this might be if you are restricting your analysis to, say, the very early phases of some huge adaptive radiation. But then you could always go in here and alter that. So what it's going to do is basically set a turnover rate that's going to have a just a uniform distribution. And what it's going to set it to is the extinction will be keyed from this. And whenever you see this colon equals in RevBayes, this is going to be a variable that will be automatically updated anytime the variables to which it's being equated are going to change. So basically, we're saying extinction rate is going to be turnover times speciation rate. The extinction rate will be automatically changed every time either the turnover changes from this set of moves, or the speciation rate changes from this set of moves. And we're also then going to sort of set up in line for our MCMC. We're going to shift the turnover rate just following a simple uniform distribution. Our sampling rate, we're going to do the exact same thing. Some big moves, small moves. Again, the sampling rate looks to be pretty low on these guys. And again, that's not too surprising because with echinoderms, it's not just a question of finding the plates. As any echinoderm worker will tell you from the Paleozoic, you can get a ton of those. It's getting them together so you can actually tell what you're looking at is less common. So it's going to set up moves for that. But again, although we're going to be adjusting these things, at least the initial seed numbers we have some empirical basis to them. This is our final sampling rate. This is for shifting around the origin time of the clade, and it's basically going to follow a uniform distribution. It's going to get down to about 42 million years before the last appearance. What I did there was simply use Dave Bapp's method from his Cal 3 approach, and basically gave it to what would be like a log 15, a log 15 difference. You would be basically having a really, really implausible deep divergence time, taking it back to about the Ediacaran, within the synktons. So this wouldn't just be like for echinoderms relative to everything else, within just the synktons to get that far down. So I'm basically just telling you, don't even bother looking that far down. And then this whole bit here is going to set up sort of how RevBayes is going to hold in its head this module types of changes it's going to make. This is where it's actually going to set up the tree, and it's going to take into account the fact we have our FBD distribution. Again, that's our origination, extinction, and sampling, with the extinction being changed not independently, but through a turnover parameter. This, for those of you who are more familiar with general phylogenetics, is just different types of tree changing moves, which are going to be affecting, I should say, cladistic topologies. The tree pruning chart, where you basically like take this clade here and you move it over there on the tree, sort of, you know, pick up a branch and you shift it someplace else, versus the nearest neighbor interchanges, which is where you might have a set of relationships like this, and you would flip these two, and oh, that hurts. You get the idea, hopefully. And basically, it's going to do these. The weights are going to give you an idea how frequently it's going to happen every generation. We're going to expand and collapse fossil branches. What does that mean? Well, you can take these guys here and say, let's see if this guy's the ancestral. We'll set it so as a branch length is 0, drop the divergence time to sometime within the lifetime of that species. Now, this is actually going to be pretty important because as you increase the number of sampled ancestors, you're actually going to decrease the possible likelihood because you have to pass through that species' character states. One of the things you find in likelihood analyses is you don't like point to one state as being ancestral. There might be one particular state that has a much higher individual likelihood, but we marginalize by basically summing over all of the different states. If you have a set ancestor, you can't do that anymore. So you're actually reducing the degrees of freedom by reducing the number of pathways and making a simpler hypothesis, which is going to affect parameter space. The ugly side point is when you do that, you also basically increase the number of varying parameters for divergence times, because now two sister species can have different divergence times because one's ancestor and the other's descendant. I like to joke that's when Occam the geologist and Occam the biologist disagree about what parsimony is. And these are going to be moves for just changing divergence times within the tree and at the very base of the tree. So we're going to set up all this tree searching stuff. So here we're getting much more into the RevBayes types of things. And we're going to start parameterizing this. We're also going to have some output information just to make it easier for you to see what individual trees have. So the divergence times for each taxon and node, the branch lengths, which are, you know, the branch durations that I referred to them earlier, and the origin dates. Between those, with all that information, you could draw out the phylogeny perfectly. It would provide you with all the information you want for your XY coordinates. Here's some other stuff I just set up to make it easier. When it spools out in RevBayes, it does it alphabetically, it seems. So I just have an FBDP set to the origination rate. Oops. And that should say extinction rate. I better fix that. Ooh. I just saw that. I'll have to go back to my R code and fix that. The FBDQ, it's not using it in the analysis, so it wouldn't matter, but that's the one that's going to flash up on the screen. One of the things we can do is have it flash up the output, so you can see what's happening as it goes. It probably slows things down a little, but if you're anything like me, I don't have the patience to sit there and not see what's happening. Anyways, a bunch of other information like this, diversification, the summed gaps, etc. This is all in this file. And what's going to happen is our main script is going to call on this to sort of initialize the paleo part of the MCMC search and to get the tree searches started. And if there are any more fluent RevBayes people out here who are watching this, send me a comment if I forgot anything obvious, and I will go back and retract everything that I said. So we've done that, and then we're going to have the one last kicker here. We're now going to set up a main Rev Bayes script. And if we're going to go back and grab our matrix. Now, this is the part where we're going to grab the file that it's going to use for the information about first and last occurrences. As I said, these days you're getting wonky results if they have different types. So I'm just going to use the one with just the FAs. And then we want the parameterization script. And I always use Harry Potter spells to label these things, so I'll know that it was me and not some other crackpot. Voila, done. So what do we have with this? Well, it outputs two different things. A stepping stones analysis and an MCMC analysis. What the hell is a stepping stone analysis? Well, that's a whole can of worms, isn't it? There are going to be lots of options on ways you want to run this, in particular, different models of character evolution. Stepping stone approach is designed with the idea that you can sort of take the different models, and what we'll do is put increasing weights on the prior probabilities, so that when we're making decisions, when the MCMC search is making decisions about what to go with, as you get further and further along the stepping stone, it's going to be based increasingly on how probable is this topology given origination, extinction, sampling, et cetera. The idea being that when we're dealing with something like a character evolution model, if it's a generally good model, it should be coming up with a lot of trees that have high prior probabilities, but that also have high likelihoods. And what we can do is basically sum through these and sort of basically marginalize all of the phylogenetic and diversification stuff. And I guess maybe the best way to think of that is if you were to if you could somehow take the likelihoods or the posterior probabilities of all your hypotheses and somehow plot them out on a single axis and do it so it makes a nice bell curve. There's sort of two different options, different ways you can look at this. And what the MCMC approach is about, and related ones, is looking at the areas under the curve, under the idea that good models aren't going to produce not just the best one. All in this case, say we're contrasting a uniform rates of change versus log normal variation amongst characters. So all characters at the same rate versus they're following some log normal distribution. The peak hypothesis in this dummy example, the best one is going to be the log normal, but it's not just that it's the single best. It's producing a range of really good hypotheses relative to what a uniform rates is. Part of the idea with the stepping stones is when you're getting generally good hypotheses, what they should also be doing is coinciding with a lot of hypotheses that were already apt to be true in the first place. So we can sort of contrast the character evolution models that way before settling on one we want to use for the full-blown phylogenetic study. I mean, one way I like to think of it, stepping stones would be really great for things you might want to publish in paleobiology, where you're contrasting different ideas about rates of change or something like that, because what you're effectively doing is marginalizing phylogenetic uncertainty. We'll never know the phylogeny, right, or all the exact details, but you're taking into account there was one there. And so that could be a very useful way to establish that you might have had like an early burst as opposed to continuous rates or something along those lines. Again, sort of the bread and butter of paleobiology papers. But then when you want to publish the phylogeny of your group, that's when you need to start justifying why you're using particular character evolution. So when you're writing your JP paper and trying to argue about why this particular topology is better than others, stepping stone is a way to say, okay, look, we went through these and this was the best character evolution model to use. And I should probably stop the share momentarily to see if anyone is, any of the people more familiar with phylogenetic stuff is screaming loudly. No, nobody's screaming at all. Maybe they're just screaming into a void. All right, I will then walk through what's in this script. Move you guys out of the way. So it is set up. So this is all written by R, and it's going to set up a default folder for this. Again, this is set up for Pete Wagner's computers. You will have to insert your own information in here. That said, you can insert it into the R program I just wrote, and it will work for you, assuming you do it correctly. It's going to call on, there's a scripts folder that I included on the GitHub. This is just sort of some default settings that you can use in general. Some of them will be changed below. One other thing that I had this program do that I didn't really emphasize is this. It divided the synced matrices into three: one of 2 states, one of 3 states, one in 4 states. Well, why am I doing that? Well, because when you're playing with the MK models that underlie this, these sort of likelihood models for character change, we have this issue in that they're going to look different depending on the number of states you use. So let's say we have an alpha, which is going to be our sort of expected rate of character change, of instantaneous change, and a time of 1, and we have 2 states. If you look at Paul Lewis's paper from 2001, this is actually the example he uses. Keep in mind, this is going to be based on net change and net stasis. So what this is giving you here is the probability of going from 0 to 1, either by going from 0 to 1, or from 0 to 1 to 0 to 1, or from 0 to 1 to 0 to 1 to 0 to 1, et cetera, et cetera. Basically, the probability of any odd numbers of changes. Net stasis is basically the probability of no change or any even numbers that would take you right back to where you began. So that's just what the MK meant, to sort of summarize it really crudely. When we go up to 4 states, however, and the same alpha, you start to see this sort of difference in that, okay, the probability of net stasis doesn't change much, but the probability of deriving any particular state goes way down. Of course, it's almost necessarily limited to be that, right? Because if you have 3 options and they're all equiprobable, and we have the same rate of change, then we expect the probability of jumping on any one of them to be 1/3 of that, which is about what we get. Well, the difficulty is, and this is something you see in a lot of morphologic matrices, in terms of a one-size-fits-all. You have to have an MK model in which the MK, for any one character, in which K is at least equal to the number of states it has. Many morphologic matrices have distribution of states, so you have a lot of binary characters, a few 3-state and 4 states, but it's very common for there to be a small number of like 7, 8, 9, 10. And the problem is when you evaluate binaries in 3 states on a 9, 10, 11, whatever MK model, what you wind up doing is creating all of these pathways that couldn't have been. And basically, it just nukes the power of the test, because all of these different transitions become equally likely, and a lot of different trees start to get similar likelihoods. So what we need to do is separate them out. Now, in soon-to-be released versions of RevBayes, and in fact, the version you can get if you download it and compile it on your own, it will do this for you. It will basically separate out the 2, 3, 4, 5, et cetera states and set up MK models for 2, 3, 4, 5, basically do it behind your back, or basically behind the scenes for you without having to do so. The current one that you can download, you would have to separate them out the way that I'm doing. But the other thing is you might want to do this anyways, because one question of interest for paleontologists from a macroevolutionary perspective is, does this group of characters and this other group of characters evolve at the same rate? Again, this is like a topic of paleobiology papers. It's also a legitimate systematics question. When I got going, again, it's a while ago now, but the stuffy old people at the time, their questions, well, how do you know which characters are good? What about this group of characters that I think are really plastic, which my arch rival thinks are the hotline to truth? Always seem to work like that, curiously. Basically, the questions like that. And we have prior biological reasons to suspect that certain suites of characters are going to evolve at different rates. Well, you're going to have to partition the matrices to do that. And the algorithms that I have in here will do that for you in advance. And again, this is something the molecular people have been worried about for a long time. 12S and 18S, do you really want to use the same model? You want to run them on different rates. First, second, thirds can have different rates, stems versus loops, all of that stuff. Again, if you're a paleontologist, you probably heard this during some seminar and you sort of like nod and makes sense for a moment, then you forget about it. But those are really the same issues that we have when we say, you know, I think the feeding structure characters on the crinoids are going to evolve at different rates from the main plate ones or from the stems or something like that. It's just that our biological reasons for thinking these things are much more interesting than theirs. And I'm saying that in a completely nonpartisan way. Anyways, so what else do we have here? It's going to set it up so these are the matrices it's going to look at. And it's going to eventually put them all together for you. This is telling you the number of characters, the number of states that go within each one, and also our scheme. We need a different MK scheme for ordered versus unordered. In this case, everything is unordered. However, it will have read all this information from your Nexus file. Oh, and that's the other thing. RevBayes and a lot of the related programs like really stripped down Nexus files, which is probably fine for molecular people. But for those of us in the paleo world, we're often using these Nexus files from things like, well, Mesquite now, I used McLeod back in the day, as a traveling notebook. You can insert lots of comments as to why you coded things in particular ways. It's more than just a data set. It's sort of a database. RevBayes does not want to see that crap. It'll blow up if you try to put it in there. So it strips out all that stuff. But the other nice thing is this means that you don't have to do this by hand every time. It'll just do this for you. It'll also read what the out group and the in group are. That's all good information that goes into setting up the trees. The fact that we have unscored taxa, that's actually important because those can affect the priors, but they won't be affecting the likelihoods. And you're just telling which ones they're going to be. We can have among character variation. I have it set for log normal. Gamma is probably more common. I just, for personal reasons, you know, probably because of papers I wrote, prefer the log normal. But what this is basically going to do is set it up so that one of the parameters that we're going to vary is the variance amongst characters, so that, you know, in a simplest form, you can have a fast rate, a slow rate, and two intermediate rates. And you're going to say, and drawn from a log normal distribution, you're going to say it's a 1 in 4 chance that a character is evolving along any one of those rates at any particular part of the tree. So what you're doing is saying, well, we're not certain what the variance is. And we think there's variation. And in fact, you'll get a best fit log normal variance or a best fit gamma parameter, which is telling you the variance as part of the outcomes from this. But you're not pinning down any particular characters to the rates, and you're not saying you know exactly what it is. Clock models, I mentioned those before. As it's set up here, it's going to give you 3 options. A strict clock, which we all mock and laugh at, but I would point out that if you've ever done a paper about rates over time, you might not have realized it, but the null hypothesis you were testing was a strict clock. So it can be useful to think of from that perspective. I've put in 3 other options. One's for a big bang, in which it'll be a relaxed clock in a sense, in that it's going to be a clock that's slowing down continuously throughout the clade's history. An uncorrelated relaxed clock, in which basically the rates are all drawn from some log normal distribution. You fix particular rates for particular branches, and that's sort of like a model in which there's no change in constraints, but there's variation to say the ecologic parameters that are affecting things. But they're coming from some broader distribution, and you do solve for that distribution as you go. And then finally, an autocorrelated relaxed clock in which the rate of change is sort of like a continuous character on a phylogeny. So you take the ancestral rate of change and you increase it or decrease it a little bit. You know, like it's a morphometric character or something like that. I'm not really sure what macroevolutionary models that really fits in with. The closest thing I can think of, and maybe Ree can tell me if I'm smoking crack on that or not, but some of the models have been suggested with like Cambrian trilobites, which show that the integration patterns, which are, you know, fairly strong amongst species, are fairly different amongst relatively close related species, which is weird. But you don't see that in later trilobites or most other things. And if you're having sort of a constant shift in integrations, you might see small increases, small decreases, you know, starting from an ancestral point, but you know, basically moving like that. It's not as obvious of one, but it does have those options. And where that'll be important is down here, because what I've set it up for you to do is just to get these things executed, and it'll do a slightly different execution depending on what clock model you've requested. And it will then go through, and it's going to start the MC. And just to help you visualize that, probably should have shown you this earlier. I mentioned the idea of like morphometric characters. The way I find it's best to envision what an MC is doing is it's like a continuously evolving, continuous anagenetic change for a bunch of morphometric continuous characters within a lineage. Part of the MC is we will have multiple chains, but each of those would be its own lineage. And you have parameters like the cladistic topology, the branch durations, which would actually be a vector because that's going to be one for every branch, the average rate of change, the rate variation, origination, extinction, and sampling. Every time you change one of these, you're going to get a new likelihood if you're changing the rates, actually, or the branch durations, and a new probability if you change the branch durations in cladogram or any aspect of diversification. So again, you can think of that as like some, like one of Gene Hunt's ostracods, getting small little changes as you go. We're also going to have a selective criteria on this. And basically the way it's going to work, there are options in Markov chain Monte Carlo analyses where you can always have a better proposal. So each of these hypotheses here is a new proposal. They can be really, really similar to each other, but it's going to have something different. We'll always take it if it improves things. But if it makes things worse, we might take it with basically by rolling a die and the ratio between the new likelihood or the new posterior probability and the old one being the key. And the reason why we want to do that, again, is going to be one of the other differences between this and most other search algorithms. There are two related ones. And that's the idea that if we have complex underlying mechanisms that are more complex than any of our hypotheses, we're going to get this sort of what they call an island effect, in that you'll have multiple peaks based on very different combinations of parameters. If you have what's called a greedy algorithm, if you start off on this hill and only take things that get better, you can only go up this hill. You can't find this other hill over here. By relaxing the criterion and occasionally allowing allowing for worse hypotheses, you have the chance to sort of drift over. And again, in evolutionary terms, I think the best way to think of this is like a Sewell-Wrightian model, where you have some drift from one adaptive peak for whatever reasons, where a new deme, a new population gets close enough to another one, they can start evolving in that direction. Under a greedy algorithm, that can never happen. Under an MCMC, there is a chance you can get over here and thoroughly explore that space. And again, this is going to become important because the way we're going to compare hypotheses now is not the king of the hill, not the single best, but sort of the size of the hills that we're dealing with. So all that stated, this is where we're going to start setting this up. When we do the source here, the moves, this is where we're going to be adding in the part that says, okay, here is our MCMC ostracod, and this is how we're going to be having these three parameters evolve, as well as setting up how these two parameters over here, the branch durations and cladogram, are going to evolve. The scripts for setting up the character state evolution is going to describe how these two are going to evolve. And then we're going to go through with our searches. The monitors command is basically going to tell you what to output to the screen, what output to files. Cats here is going to tell you, because it's a stepping stone approach, how many different stepping stones. Each one of these, if we have 20, is going to get 1/20th of the way further to completely ignoring likelihoods, starting from 1 going to 0, although it doesn't follow a strict linear decay. This is more MC babble. For burn-in generations, that refers to the fact that when you first get going, you're going to be making a lot of big improvements. You don't want to be saving those trees or those hypotheses and including them in this part down here. Ideally, you want to get to the point where you converge and get what they call the fuzzy caterpillar. When you plot them out, the posterior probabilities be zigzagging all over the place. What that really represents is you've hit upon a good solution. When you make changes, it drops down, but you don't keep them. So you go back to that general solution, and maybe you make some slight improvements, very, very small ones, with some of the tweaks that you keep. You're basically hitting upon the same general thing over and over again. And this is where I have it set up. And again, I really have the setup in mind for the beginners because there are a lot of other models you might want to look at. Again, I would refer you to a proper RevBayes or proper Bayesian phylogenetics tutorial for that. But it's going to output all of this stuff. It's basically going to execute the stepping stone analysis depending on which of the character evolution models you had. And the important is, why I have it set off, is it'll output different named files. So you don't make the mistake of, say, doing your strict clock, then you do your early burst, and you accidentally use the same file names and erase what you had before, because I've done that. You don't want to do that. It's not fun. And then, of course, just sort of finishing off depending on what you had. And these would be the parts that would be important for giving you the information to let you get the idea of which model you want to go with in the end. So you then would find a RevBayes tutorial, execute that, and voila, the magic begins. Now, at that point, I want to stop because there must be questions. Aha, yes. Oh, thank you. Mark is here, but he's, Mark did ask us, oh, I think I got that, how they're asked initially. And yes, David Beth is probably right about how William, Occam, the geologist and biologists would have gotten along. The island effect, yes. There are older papers going back to the 90s. This is actually turned up in parsimony searches. And one of the reasons why, if you've ever used PALP, it gives you the alternative for doing, like, say, 100 iterations with a randomly generated tree, was just that. It wanted to give you a chance of starting off with a different hypothesis base. And because it's going to be a greedy algorithm and just go uphill, you had some chance of finding the different hells. And it would report the different islands. These would basically be collections of trees that you couldn't get from one to the other with just climbing. Now, the huge difference is in PALP, at least when you're doing the cladistic searches, the only thing that it's varying, oops, going over here, is this, cladogram topology. The branch durations aren't considered important. The rates of character change aren't considered important, et cetera. None of this other stuff matters. So it's only varying one parameter in the first place. Now we're going to be varying a whole bunch. As I said, the difference in looking at this is you're not asking about sort of simple phylogenetic relationships. You're actually asking ideas about evolutionary histories. Phylogeny is one key part of that. And again, going back to the original basis for it, because the first and last appearance times are going to be critical in affecting how well these parameters, what prior probabilities are going to be from these parameters on a given tree, and of course for affecting the branch durations. That's why we want to be able to use the paleobiology database to, or something like that, to get at this. And let's see here. Yes, a couple other things. It's similar to the parsimony ratchet. I'm sorry, I've forgotten what the parsimony ratchet is. I remember that was a 90s kind of thing. I mean, the one thing that they did do, that Swafford did put in, I remember, to get there, was basically lowering your threshold. So you'd keep all trees within, say, 5 steps. But it's a little bit different because it was entirely deterministic. So you would just keep trees of a certain length. Here it is entirely probabilistic. There is some probability after any switch, if it's a worse tree. or worst hypothesis, I should say, that you'll keep it. Now, some Markov Monte Carlo algorithms will go the whole hog. So even if it's better, there's still some chance you'll retain the older, worse ones based on the same criterion. I don't think RevBayes is one of those, though. And I'm sure there are detailed statistical papers in which they use all Greek letters inconsistently throughout that argue about the merits of one way or the others. I've never been able to get through them. Yeah, there is the issue of, if you hear the phrase about reversible jump MCMCs, what that is referring to is situations where you're changing the parameter space. So if you collapse a sister species into an ancestor, you've changed parameter space that way. Now it looks like I'm flipping you all off. I didn't mean to do that. So I'll do it like this instead. Apologies. That's going to affect the parameters because we now have one fewer freely varying nodes. The other time you can get this, though, is by collapsing things into a quote-unquote hard polytomy, which has been suggested as an actual true pattern for things like species flocking, when you have divergences that are happening faster than you actually stop interbreeding amongst groups. It's been proposed for things like cichlids, most obviously, but there are other cases. The issue about the MK models and why to separate them is basically, if you have a matrix in which one of your characters has, say, 9 states, your binary characters, presence, absence, or otherwise, are going to be evaluated based on a 9-state model, if you use the same model for all of them. And that means it's going to be looking at the probability of getting all of your zeros and ones at every node, not just from 0 or 1, but from 2, 3, 4, 5, 6, 7, etc. And what this creates is a situation where you're adding a ton of different pathways, and it becomes really easy to actually generate almost any topology at fairly high rates of change. Because basically you're saying, if we just yo-yo everything around at high speeds, your probability of vector is just 1 over whatever the combinatoric is, or the number of possible combinations. So that's the reason why we've been separating it out. This is not a trivial issue because it's a variant of what we call ascertainment bias. So the script that I had kicked out, and actually I'm going to go show you this again really quickly. And where were we here on this? Coding bias. Now, if you're doing molecular sequences, you get, say, 1,000 sites, and you dump them all in. If you ever look at one of them closely, you'll notice that most of the sites are actually invariant across the entire group. But you know it was there because the site's sort of a real observable thing. With morphology, it is sort of difficult to work out that you had a homology that could have varied if nobody's showing any variation in it. There are sort of ways you might be able to do it with like extended outgroup analyses and things, but you're basically just sort of adding more and more taxa to look. If you don't have any, if you are not coding invariant characters, if you're not coding on apomorphies, this is something that the MK algorithm wants to look at, because what it wants to do is essentially take into account the fact that there are unsampled characters. In fact, the way it does this, it again goes back to sampling things we play with in the paleobiology database. The correction for it is not dissimilar to using like a Chow-2 correction to get at unsampled species. And what you're basically going to treat those as is it's basically like taking into account you have these, say, 3 or 4 additional characters that were invariant. But when we're worrying about the particular models, we now have to have those characters show 0 net change throughout the entire tree. Now, what's going on here is, why do I have all variable? What that's reflecting is the fact that in this matrix, there were odd apomorphies coded, and there were some invariant taxa coded. And that sometimes happens. It does, you know, some workers are better at just sort of leaving everything they code, but for a long time, people were just deliberately culling them out of the published matrices. It's always struck me as a little bit of a short-sighted idea, because let's say you do get an odd apomorphy for this species. Well, you know, it might not affect that analysis, at least in parsimony, but the next museum you go to might have specimens in a drawer where you see that new state on another species. So why not record it and go with it? And plus, it also expanded the other things you could do with it, looking at rates, morphospace, et cetera, et cetera. But for a while, back in my youth, they said, oh, don't do that. It'll just slow down searches and everything. So it was not always done, but it's something it needs to take into account. So it's basically getting these scores by looking at the 2-state, 3-state, and 4-state matrices and asking, are we seeing, in this case, we're seeing only variable coded characters. There are no odd apomorphies. There is no invariant. And in fact, it's kind of, logically difficult to think of how you're going to recognize a 3- or 4-state character that is invariant. In case you're wondering, those characters that are invariant are automatically assumed to be 2-state under and the way this is splitting things up, because I'm not sure what else you could assume about them. But that then becomes important when we're looking at numbers of states, because the question is, we've seen 3 states. How do we know there wasn't a 4th? No one, insofar as I'm aware, has tried applying the ascertainment bias issue to states within characters. Maybe the good Dr. Baps can correct me, or others who might be there. I'm not seeing anyone saying, you dummy, you didn't read my paper. Woohoo! Okay, so at this point, you could run this and you could be ready to go to town in the Synctons. It's not always going to be this easy for a variety of reasons. So what I'd like to do is give you a quick example of how you can do things when the data matrix isn't really matching what the Paleodb has in mind, but also a system, because you might be thinking, well, I've got all this data I've collected, particularly like you're a graduate student, and you have a lot of data you've collected from the field or from going through museums that you're not quite ready to share with the Paleodb and the rest of the world yet, which is completely understandable, but you want to include it in this. So what I'd like to do real quickly is show you how you can do that. This is going to be an example with Ordovician trilobite called the flexicalamenes. This is based on a data matrix by Brenda Hunt and Nigel Hughes from like 2007. I should point out the Syncton stuff was based on work by Andrew Smith and Samuel Zamora, plus been augmented by additional papers by Samuel. So give credit where credit is due. So same sort of thing. I'm not going to save the files. And we're going to go grab ourselves a trilobite data matrix. And it's getting taxonomic data. Uh-oh, wait a minute here. 2 of the taxa do not have any occurrences in the Paleodb. Oh, woe is us. Well, one of them is Gravicalamini, or however you pronounce this. I keep wanting to say Calamari, but that's not right. Gravicalamini species.
Pete, you're going to want to share your screen. We can't see.
Oh, I'm not sharing it. Did I take the sharing screen off? My fault. My bad. Yep, I did. Sorry. So I just ran this. Sorry about that. Same thing. We changed the group. Ordovician, Flexicalameini. We're now grabbing trilobites for the control taxon. We changed our zone taxa to conodonts and graptolites. Much of the rest of it is going to be the same. And when I executed this, I'll just redo this really quick because it didn't take much time to tell us that we had a problem. It's getting the taxonomic data, and it's telling us that 2 of the taxa in there have no occurrences in the Paleodb. Now, there are a few reasons why this could be. In one case, it's going to have a really tough time finding this. And there are other situations where you're going to get that. This is really common in the vert literature. Here is a matrix of titanosaurs in which the OTUs, some of them are just given as specimen numbers. There are some of these dinosaurs that have been in matrices since the 90s for which people are still using the damn specimen number. I guess like George Martin must be the one in charge of describing them or something, because dudes, what's the hang up? Like, put a name on that thing. But this isn't the kind of name we stick into the Paleodb. Or if it is, there are ways of entering in vague IDs with things like specimen numbers, specimens indent, et cetera, et cetera. It's a very low probability they're going to choose this same format. Because remember, this is a computer. I'm asking it to look at strings. Computers are sophisticated idiots. They do what you tell them to do, not what you want them to do. And although a person would recognize many iterations of this as being the same thing, a computer isn't. Well, how can we deal with this? Oh, and the other one here is subspecies. Well, haha, we don't really do subspecies very well with the Paleodb. So it's looking for, and moreover, here's an additional problem. There are ways to sort of trick it into reporting the occurrences of subspecies. When the subspecies is not named, subspecies epitaph is not the same as the species epitaph. When it's identical like this, it's not going to be easy. So what can we do here? Well, what I've done is created what I'm calling a bogarted file. I love silly, outdated cultural references. And what I've done with this is set up some relevant occurrences. And I've done a couple of things here. Here are the names. So here's Returza, and Returza minuens, which could be useful to separate out. Here is Gravikaliministpa Ross 1967. Now, here are occurrence numbers. What these are actually the occurrence numbers that go with particular occurrences in the Paleodb. I'm going to use this file to re-identify them so they'll have names consistent with what the Paleodb has. And here is the collection number that goes with it. This is basically a lot of the information that you'd have that goes into the Paleodb. It's all going to match up on the files. Moreover, in my intrepid searches, this is based on a British Geological Survey, sort of just one of their survey reports where they're summarizing different taxa. They're different places. A lot of this is stuff that doesn't make it into journals or anything like that. It's often stuff that you can find attached to specimens in museum drawers and that sort of information. But I want to add this in because this species is in here, and I want to get every occurrence I can. So what's happening here is when I'm editing Paleodb stuff, I'm putting in the collection number and the occurrence number. When it's just my, bogarted stuff that I'm not sharing with the world, it doesn't have this. It will go through and sort of add these on later. You are going to lose some of the subtleties on getting the Paleo-Latin long. Chris Scotes used to have a program that would let you get Paleo-Latin long from modern coordinates from particular points in time, but I don't know if that program exists anymore. The Paleodb will do it using Scotes' algorithms, but I don't know if it's available as a standalone program. But what we can now do is grab this, and I'm going to change this to bogarted equals true. Go grab this file again. Flexicalamines. Now adding my private stash. Now it's doing all the same stuff it did before. We now have occurrences for everything, for all of the taxa that are in there. And it's going to take a little bit longer to do this while it cranks through because the trilobites are a bit bigger of a group. We're getting most of the Ordovician. But what I've now been able to do is augment the Paleodb data with my data. I've also put in things so you can set up so you can sort of personally for your own purposes, edit some of the stuff. So if you're going through this information that we had before with, say, the Synktons, and you wanted to make some changes for your own purposes, but for whatever reasons, you did not want to share that with the rest of the world quite yet. And as I said, if you're like a graduate student or a postdoc, you're still working on these things, you do have legitimate reasons to want to bogart your data. You can add in the changes that way. You can also, as I said, include the stuff that you personally have collected but that you haven't gotten around to publishing yet. And that's going to be critical because now you can then combine it with all the Paleodb stuff, get that extra information. As I said, we're going through here and now we're getting the occurrence data for all the conodonts and the graptolites. We're going to sieve that down to just those collections that have the relevant trilobites in it. And I make the stuff happening song and dance music. Now we're refining it with the external rock database. Hoo-ha. And so this all goes by relatively quickly. when you're doing really, really big, like if you're doing like all trilobites for the Paleozoic, this part would take a bit. And then, you know, just downloading all that data from Dailydivy site wouldn't be all that quick either. But it goes by relatively fast. So, yes. And actually, at this point, I'm going to switch it back because it is just going to be sort of rehashing what we had before. At this point, it's now trying to refine it a bit using Allroy's algorithm, etc. But this is, oh, right. Mark pointed out that Paleodb uses Geoplates as the default. I have this algorithm set up to this particular function that I'm using. You get to decide. You can put in SCOTs or you can put in Geoplates, and it'll do whichever one you pick. I have it set up for SCOTs simply because, particularly with the with the Ediacaran and the early Paleozoic, there are a lot of places where it'll just not be able to find the coordinates or the geoplate, which tectonic plate it's on for whatever reason. So I've just been sticking with SCOTs. But yes, Mark is correct that it is the default. It'll be geoplate. And let's see here. So at that stage, we now have all of this information that I showed you before. We just repeat the whole thing with setting up the RevBayes scripts for the flexicalymines. We'll have all of that same information there, but in addition to the Paleodb, we'll have augmented it with your own private data. So along those lines, those are the basic things. I had one other example that I could show you that I set up with plants, in which is a study of mostly Devonian and Carboniferous lycopods, but which they also included like some very recent things. And it's basically the only augmentation is you give it a file and says use just this subset of the taxa. So it uses only the Devonian and the Carboniferous ones. And from the perspective of phylogenetics, I would actually be a little concerned about trying to connect taxa from hundreds of millions of years later without any information about the taxa in between. It would certainly violate a lot of the assumptions that's going to something like RevBayes about the expected tree shapes given the distribution of taxa from the Devonian and Carboniferous, and why aren't you finding anything? It doesn't really have a way to take into account the fact that we don't have any Permian through, I guess, you know, late Mesozoic lycopods, because I just didn't bother to add any of them. So it was just a way to cull those out. And now that's something you can actually do a little bit more easily with your Nexus file in advance. You can just eliminate those and run them, and everything will be fine. I do like to provide these options simply because, as I said, if you're a morphologist, there are aspects of that Nexus file that's sort of sacrosanct, because that's where you're probably keeping a lot of your notes and a lot of your discussions of things. So if you start dividing that up into multiple matrices for multiple purposes, you'll get that nightmare situation and begin editing the wrong one, and it gets really hard to go back and combine the info. So it's just sort of a, you know, based on my own personal experiences, the way I'd rather do things. But it is nowhere near, I think, as important as being able to augment the Paleodb's data. So along these lines, do any of you have like scenarios in your head for types of data you would have? You know, you have your Nexus file. You've been coding diligently. You know about the Paleodb as one resource. You might have ways to adding other data. I would be surprised if you're not thinking, but I have X. So what I want to hear from any of you, are there any other sort of X's? You know, I have this, and what you're doing isn't taking that into account. Because much as I'd like to think I'm omniscient, I'm not. Man, I'm really getting bad quarantine hair. Looking like Frodo 50 years later. Is that really it? Well then, as I said, you should have the GitHub site for getting at this. Oh, is Dave Bapst raising a hand? Did you have a question, David? Oh, that's from a while ago. Oh, sorry. I just got you. And the problem is there's so many names up here. I have to like scroll through.
That was, yeah, that was when I was trying to get you to share your screen.
Oh, yeah. Sorry. Yeah.
I've been so used to being manually muted by people running sessions that I hadn't even considered unmuting myself.
You always have my permission to unmute yourself.
Oh, okay. All right. I buzzed my head. That was my solution.
Yeah, I was about to say, wow, that's a rad cut, dude. Wow.
Yeah.
Yeah, I think people must love it right now, like the no screens, because it's like everyone's hair is getting crazy, or non-existent.
Mm-hmm.
Let's see here. Yeah, I guess I'm trying to, one thing I'd like to say is that if you do use the GitHub stuff that I have, feel free to use those files. I guess, for like the rock database stuff, I guess I would ask that you credit me on it, but that's really all I have no objection to people using it. If you have additional rock information you'd like to add in there, I would be happy to show you how. I've focused on the Paleozoic. I have most of the rock units from the Paleodb, Paleozoic collections, and Ediacaran in there. There are exceptions from like just sort of wonkily named units, often from the Russian and Chinese literature from a long time ago, where the basically the translations and transliterations of the names have gotten very different. But it has a lot of that. I don't have very much at all for the Mesocenozoic. I have the zones from Gradestein and stuff, and a few others. Rachel Warnock and I were working on a project 2 or 3 years ago. We started it for Cypraeid, so I got a lot of that more detailed stuff for the Cenozoic, but it's nowhere near as much as you'd want.
Can I hop in for a sec there, Pete? Can I hop in for a sec?
You can hop in away.
So PBDB is in the process of getting a new geoinformatics grant from NSF, and one of the things we're going to do is link it directly to MacroStrat. So all that rich stratigraphic and temporal information will be accessible there, and we're adding in, there's a grant going right now to add in all the OSDP, DSDP data. So all that core data from ocean basins is going to be in there too. So that'll sort of enrich our data set for microfossils and enrich our time stratigraphy information without any keystroking, because it'll come straight from Shannon's thing. So
cool.
Yeah.
What I've and there's even more you'd want to be adding, in particular biozonation data, radiometric dates, and one other thing that I have not gotten to, and I'm still trying to find a way to do this for related types of projects, is actually tying information in about particular PBDB collections that are above some radiometric date and below another, because we need particular types of rocks, obviously, for the radiometric dates. Most of the times, those aren't preserving a lot of fossils. You find the fossils in layers above or below them. And what you'd really like to know is, and I should going back one more step, this is information that can be put into the Paleodb, but what we really had in mind is that this would be the radiometric date for the rock in this particular collection, not 5 meters above or 5 meters below. And so there's additional sorts of more specific linkages that would be providing sort of ideas of stratigraphic positioning. Those are additional sorts of things where I think it'd be useful for people to sort of work on outside databases that hopefully ultimately can be all be directed at Mark and Shannon for global use. But again, when we first started this back in 1998, I actually found my notebook some years back from it. We were still writing on pen and paper back then. And we had a lot of this stuff envisioned that we'd get to, and it was too much. And that's because, well, as all of you who are paleontologists know, we have to try to be everything, and it's hard to do that. but that's the sort of additional sort of outside stuff for linking data to the Paleodb that I think can be really critical, not just for phylogenetic analyses, but for all sorts of macroevolutionary studies. Oh, Nathan has a question if he can unmute.
Yeah, so I went ahead and just unmuted it. I have a data set that I'm trying to figure out how to handle, because I think there's a few different options here. The data set involves plants, some of which are known from multiple organs, so we can get sort of an organismal concept. And then there are many, many more species that are known only from megaspores and microspores. So I could include all of the species, or I could include only those that we know the organismal concept and can really get good matrix fill for the morphological matrix, and then use the ones that are only known from spores as, for example, Azala spa, and then those could help inform the priors on the age ranges. Or I could use the presence of the spores as the taphonomic control for the whole organisms that give good matrix fill. And I'm not really sure which one is the right philosophy to approach with.
Well, my thought, and David and Mark and other phylogenetists here might have different opinions, but that in terms of the right answer, I think if you asked a dozen phylogeneticists, you'd come up with not a dozen different answers, but 5 or 6. Well, but this is not, there are a few branches of phylogeny that have sort of been worrying about this. One has been the idea of consensus trees, where you're taking phylogenies from different data sources and trying to link them. There's also the issue of basically partitioned analyses when you have different, well, this comes up in the, modern literature, when you have groups, a clade where 75% of them are coded for one gene, 75% are coded for another gene, everything's coded for something, but you have situations where there are taxa that actually aren't overlapping coding for anything at all. And that strikes me as a situation that could arise there. That would be, you would definitely be increasing the chances for sort of a big rogue taxon effect, as they call it, where things can just anywhere. I don't know, these plants would be a really important group for playing with that, because you do have the leaves, you have the seeds, you have the spores, and sometimes you can put them all together, sometimes you can't.
I'm really excited to share this data set with people who maybe are a little more familiar with RevBayes than I am. I've only ever worked with Mr. Bayes, and I'm trying to get ready this summer to go with RevBayes, because the group only has maybe 5 living species, but there are dozens of extinct, some of which are whole plants, some of which are not. So I think there's some real opportunities there to explore explore different ways of dealing with these data in a kind of a manageable size. We're not dealing with a whole family or even a whole order.
In some way, though, that would also set up the potential for a very different type of Bayesian approach, in that when you have co-occurring plant parts, there's going to be the idea that they might be part of the same plant, and they might not. But it would seem to me that there should be a way to sort of set this up with some runs in which they are the same, in which they are different runs in which they are not. Now, the thing that David Bass was bringing up about sort of the reversible jump thing, you're going to be hugely changing parameters involved when you do this. So that's going to bring up the question of how you best compare the final hypotheses, or the the final models that you get. But I think perhaps thinking in that direction might also be useful, because in a way this could provide a test for one aspect of the question, and that is, are these co-occurring plant pieces parts of the same plant? That's something you guys get with the plant. I'm trying to think of when you ever get anything like that with almost any other group. I mean, we get a lot of echinoderms that fall apart, but for the most part, people don't really bother with doing anything with them unless they have big chunks of it. And it's also not like you have, when they fall apart, they completely fall apart. So you don't find like whole arms and then whole calyces not attached to each other, something like that, which is what you're running into.
Sometimes we do encounter that, but in this case, in this case, I'm lucky because we only get the whole plant or just the spores.
Right, right.
I'm not getting all possible combinations of organs, which
Yeah.
would be even more challenging. Yeah.
Yeah, I mean, in that case, though, just a spore tree and just a body part tree, because you do get spores, though, with the plant sometimes, right? Don't you
Yep,
find
yep,
ones?
I'm finding
Right,
them
right.
on.
But you do have that connection sometime.
Yeah.
And it could be that some sort of consensus type of approach between the two. You know, like one other place would be almost similar is host parasite studies people have done, where you're simultaneously doing the analysis of the two, and then there's going to be some sort of additional sort of linkage parameter that they have, because of course parasites will jump hosts, and it you do get it's almost like a hybridization across the tree. But yeah, so that's one of the other problems is biology is actually messier than phylogenetic algorithms want it to be. Little secret. Don't tell anyone else that though.
Okay. Thanks.
I mean, to my view, it's like vertebrates. If like there were a bunch of vertebrates where we only had the crania and a bunch of vertebrates where we only had the postcrania from, which in some groups is maybe the case.
Yeah, that's true. That does happen. How often, for the VPers here, how often do we get sort of headless taxa identified as like their own unique things? It seemed to me that it's frequently, I mean, like they start with teeth and then skulls and then eventually name the rest of the thing, but that could just be my bias as a snail worker. Toothless taxa. That could be, yeah, so there could be a few other Radula and opercula from, yeah, that's true. We do get that. The opercula in particular, because they will fossilize. So that's that little door that snails will slam shut on themselves. And that's actually a good point. I do have, I don't know if I ever ran those, but did have analyses with opercula included for those taxa where we had them, but then you'll get these areas where you just like a bunch of opercula and no shells for whatever stupid reasons. And it's also a situation where with snails that not all of them have opercula that preserve. It's sometimes they completely calcify it. Other times it's just this sort of chitinous thing that you really need exceptional preservation to get it. It turns out it's very common with the dinosaurs for, I guess, the postcranial bit with, I can't say that. Okay. I need my son down here. He can pronounce dinosaur names. Yeah, and when you're dealing with mixed modern data sets, that is going to be a big issue. And of course, that's going to be the same thing that comes up with the fact that, like in the bears example, they'll give you on the RevBayes side, those fossil bears, shockingly, because unless you got this behind you, we're not getting the sequences for them. But you do at least have the skeletal material coded. Oh, another TARDIS. Excellent taste. You do have the skeletal material that can be coded for the extant and the extinct stuff in common, which is nice because really it's those linkages that are going to be critical. In a way, though, there is still a lot of untapped fuzziness that paleontologists might want to look into taking into account. And what I mean by that is it's sort of uncertainty. And one of the things that I think Bayesianism is really good for is taking into account the fact that we're not certain about stuff. And instead of using sort of single points, using distributions. I refer to as embracing the uncertainty. And a lot of these issues would be different aspects of uncertainty. And this has not gotten much attention from the molecular world because they just don't really have to deal with it much. And it's more of an issue that I think we paleontologists have to take up. But again, that's not one of the things I would emphasize from this, for those of you who are attending and are still here listening, getting involved with this would be really good. The RevBayes people, I've had some involvement, and they are really open-minded about paleontological questions. The theory, they don't assume that everything works the way that, say, the strict clock people did in the 90s. And sort of the general questions, they don't know this stuff like the back of their hand. I mean, in the same way that most of us probably can't just go recite off the back of the top of our heads what the difference between a GTR model and an HKY85 with gamma. The terms we've seen and sort of know about. And for a lot of the paleo stuff, it's like that for them. These are concepts they know dimly, but they're willing to listen to it about it. And because we might be able to present them with sort of novel problems to solve, a lot of them like to help solve these problems. That's part of what they're interested in. So I would strongly recommend, if you're, as I said, I really shotgun through RevBayes part, and because I was really trying to set up how you could use the Paleodb to get going on that. There is a lot more you can learn. I would not be surprised if there's going to be some like online tutorials for this over this summer, because of course all the classes got canceled. So I would really strongly encourage people to do that. Anything else? Okay, well, the other thing I would say is if you download those programs I left and you run into any issues from them, email me. I'll ignore you. I mean, I'll get back to you when I can. I'm trapped down here in, the basement for who knows how long. So anyways, you're a wonderful audience and all that stuff. Remember to tip the people with the drinks, if there were any. And I guess till the next time we have the Paleodb thing. Okay. Later, all.